All right, we're good to go. So welcome, happy Friday. Congratulations, we've made it to the final session of the conference. So quick, everybody give yourselves a round of applause for making it here. I always like when you land in these types of sessions because everybody who is here has chosen to be here versus getting to the airport, hanging out at the pool. You might have seen a couple of bars and casinos on the way in. So thank you, and thank you for choosing to spend the time with us. I know that everybody's brains are pretty full. You've got a lot of things on your mind, so we're gonna try and up the energy just a little bit as we go through this today. And we'll walk out at the end to the tune of closing time. You won't have to go home, but you can't stay here. So quick show of hands, who do we have in the room? How many folks would identify as a developer? Okay. They all sit on this side, except for that gentleman. Infrastructure administrator. Okay, that's a fair number of folks. Architect. Anything else? That's awesome too. You're welcome. I'm glad to see you here. We're going to talk about our intelligent compute infrastructure today and how you pull together everything that we've been talking about through this week, how you deploy it, how you optimize it for performance, reliability, cost, and more. We're going to talk about a lot of different pieces, how they all come together, and show some new tools on how we make sense of all of these things. Before we dive in, I want to do a quick round of introductions. My name is Matt Winkler. I'm lucky to lead product management for the core infrastructure of Google Compute Engine and Google Kubernetes Engine, focusing on reliability, security, performance, scale, customization, a bunch of fun things. And I'm joined by Filip Knapik. Filip is the group program manager who's responsible for a lot of our VM deployment and management at scale, and is the brains behind a lot of the stuff that we'll show later. It's important whenever we do one of these things to note that we're here because of the hard work of a whole bunch of great teams from around the world. And so I'm really excited to be able to highlight a lot of the cool work that's been done. So let's go ahead and dive in. And so we're going to really spend the rest of the time today focused on three different areas. We're going to kick off by talking about the modern infrastructure challenges, or as I like to call it, why is everything so hard right now? We'll look at the friction of running and scaling and securing and building workloads, and some of the reality of the trade-offs that you have to make as you choose between speed and sanity and making your customers happy and your compliance folks happy and your finance department happy. And we want to talk about the different hurdles that you'll run into so that we can spend the rest of the session talking about how you get past those. From there, we'll move into the best practices and recommendations, which you can think of as a how-to guide to take all of these things, put them together, keep your budget and your boss and your customers happy. We've tried to distill lessons from some of our largest and most complex deployments, what we've seen from working with customers, into a roadmap that we can balance performance and reliability and all of the ilities that you need to think about. And then finally, we're going to talk about how we're moving forward from just the infrastructure to doing a lot of the heavy lifting and thinking for you. This is where we're going to show some new tools. And hopefully these are exciting and they'll be able to help you deploy and manage without as many headaches as you may have today. We will be hanging around for questions afterwards. They're totally welcome. If you've got them, just jot them down. We'll get to them when we are finished. So why is everything so hard right now? And let's look at this through the lens of the things that we're trying to do and how these are expanding. And so here's the evolution of how I think about a lot of the problems that we've all had to deal with. For a while, it was really easy to think about the discrete bits and pieces of work that we had to do. We had to deploy a service. We had to provision a VM. We had a firewall we needed to tweak, a database to deploy. There were relatively straightforward steps or playbooks, and they tended to follow the happy path of the tooling. The question was not, what do I need to do? It was, hey, I know what I need to do. There's just like, how do I go and do it? How do I do it quickly? And then as we get more sophisticated, how do I automate that? How do I make it repeatable? Now, as things started to get more complex, it's not just about the individual component. We needed to deploy and manage an architecture of a variety of services and components. It wasn't just enough to deploy that. We had to configure it, tune it for trade-offs, handle security requirements. We had to move between the applications, the infrastructure, the workloads, between all three of those in order to get to an ideal solution and an outcome. Oh, and while we're doing that, a couple of things are likely going to change. And so at this stage, we moved from playbooks and the happy path of different tooling really to best practices and standards and guidance. We wanted to wrap this up with policy and governance to make it easier and repeatable and consistent. And then we started to do things like infrastructure as code in order to make that reliable, deployable, editable, and whatnot. Today, though, when I talk with customers, fewer and fewer problems look like the left-hand portion of the slide. They look like the right-hand portion, which I'm not going to read, but I imagine this is somewhat familiar to you. You're being asked to balance performance, workload specifics, details of the workload, resiliency, compliance, cost, the topology of a solution, where you're going to deploy it in the world, how you're going to deploy it and secure it. And you're going to have competing priorities. You're going to hear that, hey, it needs to be faster and cheaper and resilient to failure. And my security team has a bunch of requirements. Oh, and by the way, it needs to be cheaper. And, oh, but wait, if it's too cheap and it doesn't scale in the time when I need it to scale, that's not also going to be good. And so we're trying to optimize this multi-dimensional problem, and each component that we're incorporating is adding an ever-increasing amount of knobs and dials, right? Every session you probably went to this week, there was somebody standing up here really, really excited to talk to you about the details of a single thing that's being built. And those are awesome. But we're all being asked to take those and pull those together and into a solution. And so in a complex system, you're not expected just to understand how the individual components work, but as I put them together, how are they going to all interact together? And so what are some of these architectural goals that we're shooting for? We joked on the last slide a little bit about cost, but cost is front and center. You want to optimize your spend, you want to run things efficiently, but you need enough headroom so that as you scale, your customers get served and don't experience downtime. So you have to have the right capacity in place. Performance is going to matter at every layer of the stack. This is getting increasingly important, whether you've got a latency-sensitive workload or you're trying to optimize for maximum throughput in a batch system. You're going to spend a lot of time at each layer of that infrastructure in order to get to a highly performant solution. And then finally, everybody's workload really, really matters, right? Like, these are important things for you, for your customer, for the business, and failures are going to happen. And the time to manage these is as we design and deploy a system up front, so that as those failures happen, whether that's because of a faulty deployment at the app layer, whether that's because there's an issue in the infrastructure, or a network cable somewhere in the world gets cut, we want to design for those today so that when it comes at 3 o'clock in the morning, you can get that up and running as quickly as possible without trying to figure it out at 3 o'clock in the morning. So cost, performance, reliability, these are three things that we need to think about across all of these solutions. And so as these come together, we talked about each layer of the infrastructure has more ways to configure, more ways to optimize, and we're trying to think about this interconnected graph in our heads. And it's super easy when nothing is going to change, but when a new model gets deployed, or when the latency that was okay last week spikes or is no longer sufficient, or a new set of security requirements come down, how are we set up to make these changes, and in what tool set do we use? And so this is where we think we can bring the power of agents and LLMs to help. This confluence of complexity and change is where we can bring together a ton of insight and knowledge that's based off of documentation and guidance and information about your deployments, both static and in real time, and the context that you bring of what's important to your teams. And our goal is to bring that knowledge and expertise to you where you're at in the tools that you're using. So whether that's in an IDE for the developers in the audience, like Anti-Gravity, whether that's in Gemini CLI, whether that's in Google Cloud Assist in the Cloud Console, or if you're using something like VS Code or Claude Code, or you're building your own experiences on top of things like our MCP servers, we want to bring all of this knowledge to you so that all of those problems are always right. You've always got a way to get an answer right there. And so I'm kind of excited. We're talking about Compute Advisor. This is a specialized capability that you can think of as your own personal infrastructure architect and engineer agent. We're embedding this directly within the Compute Engine and Cluster Director consoles So that deep domain expertise that I talked about developing is always right there. And this isn't just a chatbot. It's not just trained on the docs. We've grounded this deeply on top of Gemini and Gemini Cloud Assist. And we've tuned this for all of the concerns of infrastructure at scale. VMs, GPUs, TPUs, Kubernetes, storage, network, how all of these things come together to really work with you and the intent of what you're trying to do to get a production-ready stack that you can deploy and manage. It needs to be resource aware, so it needs to know about your environment. These agents are going to leverage your specific project context and constraints so that the recommendations that you get are useful to you and what you've deployed. You don't want to just hear about a general way to scale your compute layer. You want to hear one that's relevant to the way your architecture is already deployed. And then finally, we have a Canvas UX where we're trying to move beyond just text responses to an interactive experience where you can work across all of these different complex artifacts, like the architecture recommendations. You're going to have playbooks and step-by-step guides. So over time, this intelligence is going to get integrated into the broader Gemini Cloud Assist interfaces. It's going to show up across all of those canvases that I showed earlier so that you've got this in your environment. We'll take a quick look at what this looks like. Filip will be spending a lot more time in the rest of the talk highlighting this, but let's give it a quick spin. So I'm here in the compute overview, and this lets me get started asking about, hey, I'd like to deploy Gemma 4, and what's the infrastructure that I need? This is going to swap into a full screen canvas where you can see how we're thinking through the problem. You'll get to the output, and we're not just looking to have a chat experience here. There's a lot to consider, and so we can't just simplify an answer here. We want to get context. We're going to show you your different options. We're going to then surface a recommendation, help you understand the trade-offs, and then we're going to go ahead and give you the tools, whether that's the code to copy and paste. We're going to let you click and deploy that via the cloud console into your environment. And so we'll talk about this a whole lot more. So I'm going to hand it over to Filip, who's going to start deep diving into designing for cost efficiency.
So as Matt mentioned, a complete application design needs to very carefully merge different aspects of requirements, including performance, including availability, and also cost. Let's start with cost because it is a very sensitive topic, especially in the world of AI acceleration and large deployments. First of all, let's look into some of the best practices around cost efficiency in infrastructure before we look into how Compute Advisor can help you out in those areas. Starting from right sizing, so essentially provisioning only as many resources as you need for your particular workload, hitting a sweet spot between cost and performance. In the world of right sizing, one of the obvious solutions that customers turn to, especially for workloads that need to respond to changing business scenarios and varying load from their workloads, is autoscaling. Within the autoscaling world, we have various options. If your deployment is based on virtual machines, you would typically rely on managed instance groups with autoscaler that can actually respond to various signals, including your custom ones. In the world of containerized workloads, you have obviously GKE with multiple autoscalers available out of the box, horizontal pod autoscaler, vertical pod autoscaler, depending on what your application is capable of handling, and obviously the autoscaler of the cluster itself in the form of cluster autoscaler or GKE autopilot that actually takes care of those topics on your behalf. Not all applications can autoscale though, and sometimes you need to provision static infrastructure with individual virtual machines of a set size in a way that stays in a constant way. For those cases, you may also have cost efficiencies achieved through, for instance, custom machine types. Not always your workloads can fit perfectly into the t-shirt sizes of existing machine types. And sometimes by tuning the CPU or memory settings of your deployment, you can actually fit way better when it comes to workload requirements and available size of the infrastructure. So another option to consider in case of static workloads. Moving on to the world of GPUs, there could be cases where a single GPU may be too costly for a particular workload and maybe actually too much of performance, too much of capacity for what the use case is trying to achieve. One of the great features to look into for those types of workloads is multi-instance GPUs, which allows you to share a single GPU across multiple pods in a GK cluster and therefore reduce the cost of an accelerator across multiple workloads. Moving on to a different aspect of cost efficiency. So we talked about right sizing, but there are also some options you have around the way you deploy your resources or commercial models that can help you tune your costs. Let's start with spot VMs. Imagine cases where you're running a batch workload that can very gracefully handle occasional downtimes or restarts. Spot VMs are a great way to save money on those types of deployments by tapping into available capacity when it's there and reducing your cost of those workloads. So highly recommend to look into those options, again, for workloads that are capable of handling those occasional downtimes. The moment you have relatively static load of particular instance types across your project or across your organization, you should consider committed use discounts, because this is a way for you to commit to particular capacity for those instance types, at the same time gaining cost advantage from this commitment. Another option to look into for cost efficiency is DWS Flex Start. Imagine a case where you have to fine-tune your AI model within the next week, but it doesn't have to happen on Monday. It can be any day next week. And you can create a request in DWS Flex Start, so Dynamic Workload Scheduler Flex Start, and request capacity for your GPUs sometime next week. And at the same time, you're actually gaining two advantages. You're getting guaranteed that those resources will be available when you need them. And second of all, you're also getting financial advantage or cost efficiency by tapping into capacity that is, let's say, more available at the time when you're being provided with it. So again, highly recommend to look into this feature, again, for workloads where you have some flexibility as to when exactly it's supposed to happen. So these are just some of the examples of features you may need to look into to gain additional cost efficiency. And actually, if we wanted to focus on cost efficiency alone, we could spend the next 20 minutes talking only that. But that's not the point. What we wanted to show you here is that you have a lot of various options, and the list is way longer than that. And the whole challenge is in which of those options to pick for your particular workload. How do I translate my specific use case, my requirements, into those options or many, many others? And let's have a look into Compute Advisor again and how it can help you in some of those questions. So now we're asking a question that is very specific to cost. What GPU options do I have for cost-efficient Gemma 4 31B fine-tuning, no quantization? I'll be running it once a month, provide a complete implementation guide. So we're actually asking for two things. We're asking for cost efficiency recommendation and also a complete implementation guide. Obviously, as you can see right now, there's chain of thought processing behind the scenes working on our request. We actually got an answer, and let me pause for a second. So first of all, we requested fine-tuning of a model that has 31 billion parameters with no fine-tuning. So that translates immediately to 62 gigabytes of VRAM that are needed. So from the most obvious options that a user would typically consider in this case, there is L4, A100, and H100. L4 already is below the threshold of available memory. It has 24 gigabytes, and we need at least 62 for the model itself, plus all the overheads and additional optimizations. So the model actually, what happened behind the scenes in here is Compute Advisor decomposed the problem, came up with various options of design. Within those designs, there were various options for GPUs, and then the response is provided in the context of a complete solution with the recommendation of a particular GPU to choose from. So let's have a look at the recommendation. So obviously, there is a comparison of various options with implications of each of those choices. So we understand not only the cost aspects of individual choices, but also other implications of going with one option or another. The recommendation that the model provided, which is actually the right one, is to proceed with A100. So L4 may seem, for example, more cost-effective because it's lower on the unit cost level. But at the same time, additional complexity and the number of L4s you would have to provision, which would be most likely 4 in this case, wouldn't be cost-effective. So what the model did is went through the entire exercise of how would it design this particular deployment, and within those designs compared the costs and came up with a recommendation. What we're also getting here is a complete implementation guide. So since we already requested that as part of our prompt, we're getting a step-by-step instruction on how this specific implementation could proceed. Within every code statement that is provided as part of implementation plan, there is also a variables section that that basically creates a form of all the parameters that you may want to fine-tune or change in the particular script to give you, first of all, visibility as to what are the assumptions around your resources, and also which are the things you may want to change without messing up with the code below. By the way, those values are also retrieved automatically from your existing environments. We talked about context awareness. So the names of the resources that we're suggesting in the scripts are going to follow your naming conventions. The regions are going to stick to the regions where you have most of your resources deployed, and so on and so forth. Or for example, we're also not going to recommend solutions that would not fit within the constraints of your org policies. So we are trying to be as context aware as possible, looking into your existing resources. Once I provide the input for my project ID, it is immediately reflected in the code. And again, you can take those code snippets and proceed with your implementation moving forward. So what you're seeing in this specific demo is that not only you're getting a response on cost recommendation, the cost recommendation is actually grounded in the constraints of your organization and is also taking into consideration the complete design, complete implementation that would follow. Let's move to another aspect of design, which is performance, actually very tightly linked to cost. And let me walk very quickly through some of the recommendations around performance that you should consider implementing in order to gain efficiency in this space. First of all, if you're using TPUs, one of the difficult problems to solve and one of the challenges in terms of design and architecture choices is TPU topology. And I'm not going to go to the details here because of the complexity of this space, but picking the right TPU topology, 2D, 3D, and what kind of a structure it should have is one of the challenges of these types of deployments and needs to come from deep understanding of the model you're actually going to be fine-tuning or training. Another element to consider is compact placement. Compact placement is basically how far apart individual resources in my deployment are going to be in the data center from a physical perspective. And this is essential for workloads like high-performance computing, AI, ML, or databases, because you need to have high throughput in between different elements. And actually, some of the more advanced features we're going to be talking on require compact placement to be even enabled, like RDMA. Speaking of RDMA, remote direct memory access is an essential feature for GPU, for AI ML workload deployment, because it dramatically reduces the latency of data exchange between GPUs. And this is another great example of where we have multiple flavors of this feature, because there is cloud RDMA, there is RDMA over converged Ethernet, there is GPU direct RDMA. Some of those choices are available in particular types of virtual machines, particular types of deployments, and are better suited for some use cases versus others. So it's another great example of where deep understanding of your use case and your requirements drives resource configurations and particular choices of technologies. Last but not least, from a performance perspective, is storage. We just announced rapid storage buckets that improve bandwidth in accessing objects from storage buckets for AI ML workloads. But if you want to mount file systems into your virtual machines, in clusters and so on, you should also consider other options like managed cluster or hyperdisk ML. Managed cluster typically for parallel file systems, and hyperdisk MLs for cases where you have read-only across multiple VMs patterns. So again, multiple options to consider to reach high performance from your workloads and gain efficiency from this perspective. And again, let's conclude this section with look into another quick demo of how Compute Advisor can help you out here. Let's say we want to pre-train a 70 billion model, 70 billion parameter model with time to train as the primary optimization objective. So we're not looking to cut cost, we're not looking for availability, we're specifically asking to reduce time to train, and we're asking whether TPU v5p or A3 GPU cluster is a better fit for this specific request. And let's see what the model provides in response. So we have a direct comparison of those two options that we asked about with trade-offs and pros and cons of particular options so that we understand which of the solutions is actually a better fit for our workload. Again, we have asked it specifically to focus on one optimization dimension, being performance. So it looked into various aspects and came up with a recommendation we're going to see in a second, which is TPU v5p with AI hypercomputer topology is recommended. Not only it provided that recommendation, it also gave us justification for why it thinks that is the right way to do it. So, for example, if you're looking for a recommendation for your own project, not only you're going to get a recommendation, but also justification, so you can defend some of those theses or review them or better understand them thanks to this justification as well. Let's move on to the third area that we want to highlight today, which is availability. And I'm going to start availability from what we often also refer to as obtainability, but it's part of it from our perspective, which is how do I ensure that I have access to scarce resources, to those important resources that I need, for example, accelerators, when I really need them. And there's two features, or actually more than two, that you may consider in this particular scenario. The first one is Dynamic Workload Scheduler, or DWS for short. It actually works in two modes. There is a calendar mode and flex start mode. Calendar mode can be useful in the following scenario. Let's say you would like to have fine-tuning or training of your model throughout the whole next week, Monday to Friday. You want to have guarantee of capacity throughout this time. You create an entry in DWS calendar mode to have the capacity secured in that window. And that's exactly what happens. So you basically are creating a reservation in a way, although there's probably a wrong word here, for this capacity throughout next week. Now, DWS Flex Start is for a slightly different scenario. Imagine you'd like to have fine-tuning or training for one day, sometime next week, but it doesn't have to be Monday or Thursday or any other particular day. So with DWS Flex Start, you can say, within that window, I would like to have this capacity for that long, and you're flexible as to when it's supposed to actually happen. And you're gaining two things with this mode. First of all, you're gaining guaranteed of resources within that window, but you're also gaining cost advantage because you're agreeing to tap into resources when they are in the lower demand. Okay, so again, two different modes, both very useful in different scenarios. Last but not least in this space is reservations. When you have continuous demand for particular resources, let's say GPUs, and you'd like to make sure that this capacity is always there for you, reservation is the way to go. So you're going to have your capacity secured throughout the time horizon. We talked about physical distance earlier in terms of performance. Now let's also look into physical separation from availability perspective. So first of all, you have spread placement policy, which allows you to spread individual virtual machines in a data center across the racks of the data center. So this creates additional physical separation between resources and reduces some risks related to physical problems. Let's say there is a power outage in a particular part of the data center. Spread placement policy allows you to mitigate some of those risks by spreading resources around. And obviously, traditional and well-known approaches like multi-zone and multi-region deployments are always factors to consider, which improve availability of your resources. Not much has changed in this space. And again, let's move on into another demo. So now we're going to look into availability. I'm actually asking a very specific question. I'm serving web traffic using managed instance group. How do balanced and any distribution shapes compare when it comes to availability? So basically, distribution shape in a managed instance group dictates how virtual machines are going to be spread across zones of that managed instance group. And I'm asking to compare balanced and any purely from availability perspective. Which of these two modes is better to reduce the downtime coming from upgrades and updates? That was the request. First of all, the model in here realized that I'm asking for comparison between balanced and any, but there's actually a third option, and that third option is the default, which is even. So even means all the VMs are spread evenly across zones. Any is obviously any, and balance is trying to get to even, but if it's not possible, it actually goes to wherever the capacity is available. And the model is considering those different options and how it works, and tries to look into our specific requirements of reducing downtime during upgrades and updates. And from this requirement, it concluded, rightfully so, that the balance mode is the way to go. Because even though even may seem as the right one because it actually spreads across all the available zones, the moment a zone is gone, recovery and getting back to the right capacity is actually affected, and it is not affected in the balance mode because it goes for wherever the capacity is. So from recovery perspective, and therefore also capacity guarantee, balanced is the way to go, and that's exactly what we got the recommendation here for. So again, this shows the power of deep grounding on our documentation, deep understanding of how those resources work, and therefore it allows the model to respond with proper solutions. And obviously we have all the architecture summary and how individual components play together. Okay. So seeing those examples, you probably got quite a good understanding of where we're trying to achieve or what are the use cases we're going after right now. But you may still wonder, what is the grand vision? Why are we doing this? What is the objective of all this investment? So first of all, we do acknowledge that in the infrastructure space, you need to have control over resources that you provision, and you need to have full understanding of settings that are being used in your deployments. At the end of the day, you are in charge of the infrastructure, and you need to be able to deploy your custom workloads to it. So we're not trying to create any abstraction layer that prevents you from seeing or understanding your infrastructure. However, what we're trying to achieve here is to give you an intelligent ally that is going to help you translate your requirements, your use cases, into all of those settings, into all of those configuration options that the platform provides. So basically help you decompose your problem statement into individual settings and land on an optimal solution as quickly as possible. So with that, we're aiming to create intent-driven architecture and infrastructure management, essentially. So you'll be able to convert your ideas, your use cases, your requirements, basically your intent, into deployments optimal, out of the box, as soon as possible. That's what we're aiming to achieve, and this is what Compute Advisor is working towards. Another reason why we're also looking into this right now is that there is a growing complexity when it comes to design decisions, especially if you start looking into AI/ML workloads. If you've ever done it at a scale, you're going to quickly realize that some of the decisions you've just made or you thought you made are going to be revisited down the road once you understand further constraints. So let's say I understand that my model has X number of parameters that translates to specific memory. I picked a GPU or GPUs that provide this memory, but then performance is not there. Or maybe the cost is not okay. Or maybe the bandwidth of networking options within those GPUs that I picked is not perfect. Storage comes as another dimension to look into it. It quickly becomes an iterative process with some of the decisions being revisited over and over again until you land on an optimal solution. These are the kind of scenarios we're trying to address by providing automation, by employing intelligence to be able to resolve those cases behind the scenes and help you get to the optimal solution as quickly as possible. Use cases we are supporting today with the capability with Compute Advisor are as follows. And actually you have seen many of those already in the demos. First of all, intent-based architecture definition. So you define your intent, your use case, your requirements, and we take it on and respond with an architecture guidance, with individual components, with decomposition of that problem statement into solutions that you can just take on and implement right away. That's number one. Product and feature comparisons. In many cases, with your experience, you're going to think of 2 or 3 options that you can use for this particular solution. So for example, that's my problem statement. I think solution A or B is the right one. Which of these options is a better fit? And obviously, we're going to look into that as a Compute Advisor, and it's going to respond with selection of the option that is a better fit. Complete implementation guides, you've seen examples of that already, including code snippets ready to use out of the box. How to question, how do I improve the following characteristic of my workload? How do I implement the following feature to my existing workload? These are the type of questions we're also capable of answering. And what you've also seen a couple of times already is implementation-specific guidance on machine types, GPUs, or TPUs. This is only the beginning. We're going to add more use cases as we go. But at this point, these were the ones we were focusing on. So this is the mostly initial guidance when it comes to your deployments. Let's see some additional demos that will highlight different features. Let's say we're asking, provide a complete guide for deploying Gemma 4 31B model using GKE with inference gateway and NVIDIA L4 GPU, including configuration for smart routing based on KIV cache, utilization, and horizontal pod autoscaling. Quite a complex request already. And by the way, if you think about how many docs you would need to read to get to the right solution, it's probably not a short list. So this is what we're trying to decompose and help you with by providing a response right away. So first of all, you got a comparison to an alternative solution, which we didn't ask about, but it proves, it actually confirms that the solution you were looking for, which is GKE with Inference Gateway, is a recommended one. So we're on the right track. It also provides you with a complete solution overview, what are the components to use, and what would be their individual configurations. Interestingly, it is not limited only to infrastructure of Google Cloud when it comes to the solution brief. It also provides you with some guidance on software packages like VLLM and how it should be configured to make it all work together. We're, by the way, also grounding this model on common open source frameworks that you would typically use in your use cases. So we're not limited in here in our grounding, in our knowledge base to Google Cloud services. It provides you with a response, and there is actually an interesting detail in this response. The model is also saying that it assumed 4-bit quantization in the response, which is not something I provided as an input. I didn't say what is the quantization I'd like to go with, but it assumed it should be 4. And with that assumption, it made all of those recommendations and also provided a step-by-step implementation plan. So we have all the resources being created, GKE cluster being created, Inference Gateway being configured, pulling all of the packages that are needed there, and even deployment with VLLM and inference pool lower below. But I already mentioned that I'm not necessarily a fan of 4-bit quantization, and I would like to probably provide an input into the response that I would like it to stick to 8-bit. I mean, that's my quality requirement, and I'd like the model to reflect that. And this is the power of the Canvas user experience. It's not a linear interaction. The Canvas created a document on the side, but I can still interact with it and provide additional input on the side and put additional context into the response. And I'm asking right now, assume 8-bit quantization. What's going to happen behind the scene is that this input is going to be taken into consideration, and the whole response is going to be reviewed and updated with that additional information in mind. So this creates a very nice interaction pattern of not actually getting a static response in a linear way, but allowing you to interact with the document and provide additional clarifications or inputs as needed. And in a moment, we're going to see that this additional input is reflected in the response. It just made it through. The initial part of the response hasn't really changed because the overall guidance stays the same. I mean, the architecture hasn't really changed with the quantization selection. However, what changes in the response is, especially on the solution side, is that each replica will require 2 L4 GPUs. It's actually highlighted as a change. The cost calculations have also changed, and also the step-by-step implementation plan has changed, including VLLM settings. So the script for VLLM also changed to reflect the parallel nature of the GPU structure right now. Again, the point here is Canvas is a living document. It's not a one-off in response to your prompt. It's a document you can interact with and provide additional inputs, clarifications, or context as needed to tune your response, whatever it is. Let's move on. And the last demo for today. It's actually a relatively simple question when compared to all the previous ones. For hosting a complex microservice architecture that requires automated scaling and healing, shall I use GKE Autopilot or Compute Engine Managed Instance Groups? This is more to visualize the example of I have a problem, I have ideas for a solution, which of the solutions is a better fit? And the model provides the comparison side by side, showing you which of the two options that you were asking about is a better fit for what we're trying to achieve. And the recommendation you're going to see is GKE Autopilot is a better fit, which I would personally fully agree with as well. And the recommendation is coming in a couple of seconds. So again, it goes over all of the different categories of solution that you may want to compare your guidance on. And yeah, here's the recommendation that Autopilot is a better fit. So again, this is just to show the power of looking into various options through the lens of your use case, through the lens of your requirement, and coming up with a solution that is well grounded into what you're trying to achieve. So with all that, we are starting the journey of giving you additional capability to help you manage your infrastructure at the intent level We are supporting some use cases already. We're going to be adding more and more over time. We're also going to be working on improved intelligence and even better understanding of the context of your resources. But we're super excited to launch this feature right now. It's available in public preview as of today. It is in the limited public preview, though, I need to admit. And so at this point, a limited part of the user base has access to the feature. It's completely random. There is no allow listing at all to this feature. So if you see the feature already in the console, you're part of the user base that is already allow listed. And if not, it's going to come up to you in the next couple of weeks. The feature is currently available in Compute Engine overview page, as you can see right now highlighted in the screen. It's also coming to Cluster Director in the next couple of weeks and to the GKE landing pages as well. But with that, we wanted to give you an opportunity to work on your resources in a way that is as optimal and as efficient as possible, help you navigate through some of those complexities of growing product surfaces across all of our Compute Engine, GKE, and AI Hypercomputer surfaces, and help you land on optimal solution as quickly as possible and maximize the value of the platform. So that's the vision we're going after in here. It's just the beginning, and we're going to keep adding feature and intelligence into this model as we move on. So with that, I'd like to thank you very much and ask for, if there are any questions, happy to get them. Otherwise, we can also discuss it on the site.